So we're going to talk about service code from today. So this is one of the quantum error correction code, and I'm not saying this is the most researched, but this is one of the hot topic that people are trying to understand, or at least trying to investigate more. So you can see from the name surface that this is somehow involves kind of geometric configuration of the code. So this type of code is called a topological code. So I personally think it's not about topology, it's actually about geometry. But anyway, the surface code, I'll give you the simplest surface code, and then we're gonna go through detail one by one. So the simplest surface code look like this. We have 4 qubits, and everything is qubit. And when I connect these dots by lines, that means they have some C0 or control gate put together. So the circle one is the stabilizer qubit. So this is X stabilizer, that's stabilizer. I'll draw the circuit later, so just remember the name. The circle means the stabilizer, and the square means the data. So it's the same idea as we did in the previous lecture about 5 qubit code and 7 qubit code. The data is stored in the data qubit. The actual quantum data is stored in the data qubit. We use the stabilizer qubit to detect an error. So 2 data qubit, 2 stabilizer, this is the simplest one. And I'll give you the circuit. So this is just to distinguish the register for each qubit. So this register is about X stabilizer here. Okay, so we have first Hadamard and also Hadamard for the Z stabilizer, and we're gonna put control Z and control Z here, and control X, control X here, and Hadamard. And we end this one circuit, we call it cycle. I'll tell you the name again later. So anyway, we terminate this one cycle with the measurement on the stabilizer qubits. So this shows you somehow connection between a pair of qubits, and this is what the surface code actually is, because the code quantum error correction code is about circuit and circuit and the protocol, how to detect the possible errors. So I'm going to label each step here. So this is 0, and this is 1, and this is 2, 3, 4, 5, 6. And then we'll see how measurement works. So the first step of quantum error correction, surface code, is to initialize our stabilizer qubit to 0 cats. Okay, so we don't know what the states of A and B is, so we're going to assume that A is of psi A, the random quantum state, 1 qubit state, which is A0, A1. And we're also going to assume that the initial quantum state of data qubit B is B0, B1. Okay. And then we're going to run this code, run this circuit, and then take a measurement at the end. So let's say this is, so these are initial 1 qubit states for A and B respectively, and let psi I be, so every time we run this Hadamard or control Z or control X, the state of the qubit A and B will change, and also the state of X and Z also might change. So we're going to write the entire 4 qubit state of these 4 qubits as psi I at the state I, and we're gonna order them in the following way. So we have psi X and psi Z. So at the initial step 0, psi X and psi Z is both just 0 ket. Okay? So let's compute. Psi 0 is A0, A1. Okay, so the third step, run the circuit and measure X and Z. Stabilizer. Okay, so let's compute. And yes, B0, 0, B1, 1, and then 0, 0. So when I abbreviate this, then remember the order. So the first 0 is for X stabilizer, and the second 0 is for Z stabilizer. Okay? And psi 1, we apply Hadamard on these 2 qubits, so it's going to be plus plus. Right? And then we apply first the control Z. And actually we can, okay, so let's do the step 2 and step 3 separately, and then we'll do the step 4 and 5 together. So let's see what happens after we apply the control Z on the data qubit A. So psi 2, we only apply the control Z on here. Okay, so this is the only target, so we don't do anything here. And there are going to be 2 cases. So we only because we only look at the control qubit as the Z stabilizer, right? Yes. So this one, the second plus, is about the control qubit. So is again. So if I rewrite this, so it's plus times 1 over square root 0 and 1. So when the control qubit is 0, I don't do anything. When it's 1, I apply Z gate on here, right? So everything is just the same thing as before. When I'm at this state, when I'm looking at this quantum state, so 1 over square root plus 0. But when there's another one, right, 0 and plus 1, so then I apply Z gate on here. So Z gate only changes the sign of the ket 1, so it's going to be minus. Okay, so that's psi 2. And now let's look at what happens on psi 3. So we do same thing for the B data qubit. So you can see what's happening. It's going to change the sign of ket 1 on the B data qubit only when the state is 1 ket for the Z stabilizer, right? So we can assume that this is the same thing all the way up to here, and then it will just change this sign plus to minus, right? So let me just modify this a little bit. If you're using a tablet, you can just copy paste And I'm gonna change to 3, and it's going to be minus. Okay. And then let's look at 4. So now we're done with up to 3. So now then we have to use the control X with the control qubit X stabilizer. So we're looking at the first qubit state here. So we don't care about what happens when it's 0. It's only when cat 1, and it's only about the B data qubit. So look at the first one: A0 0, A1 1, and B0 0, B1 1. The same thing. So when I expand this plus cat, then I get another 1 over square root of 2. So it just becomes 1 over 2. So we have 0 0 first, right? So that's first 0, and the next second 0. What I have 1. So I need to apply. Here, sorry. So it's about here, sorry. So it's on the control qubit. The target qubit is A, so I have to do something on here. So when it's 1, 1 0, then I change the 0 cat to 1, 1 cat to 0. So this becomes A0 1 cat plus A1 0 cat, and the same thing. Right? And then we do the same thing here. So it's A0 0 minus A1 1, and B0 0 minus B1 1. Is it right? Yeah. So AB, yes. And then 1 over 2 0 1, 0 1, and then now apply X on here. So it's 1 minus A1 0, B0 0 minus B1 1. Okay, so that's psi 4. Now let's look at what happened at psi 3. So now it's change up the target qubit. So we do something on B. So we don't do anything on here. We do something on here, changing 0 and 1. So if I change it to 5, so I'm going to exchange 0 and 1 here, and also here, right? And then, I also want to change this writing, because I don't want to write it again. So after 5, now when I get to 6, I apply Hadamard. So 0 becomes plus, 1 becomes minus. So we have 6, and these states are now changed. Plus, plus, oh my God, what was it? Minus, minus. So it's 1 0, right? So minus, plus, and this is 0 1, so it's a plus minus. Okay. So now we have to expand it and then put together in. So just before the measurement, we want to rewrite this in terms of something 0 0, something 0 1, and something 1 0, and something times 1 1. So let's call this psi, not psi again. Let's call this phi 0 0, phi 0 1, phi 1 0, and phi 1 1. So then we take a measurement. So there are 4 chances. So there are 4 chances because we had a general quantum state in the beginning for the data qubit A and B. So we don't know the probability, but generally we have 4 choices. I mean, 4 possible outcomes. And just think about 0 0 here. Suppose that your measurement outcome was 0 0. Then you'll get psi 0 0. What does that mean? Just before we think about this, we're going to compute what phi 0 0 is. Before we do that, let's think about what that is. So these things, if you look at these, it's just a pair of 1 stabilizer and 1 data qubit. You're taking a measurement, syndrome measurement. You're doing a syndrome measurement with respect to that target qubit, target gate. So if you're looking at Z and A, the first one, which means that you have a Hadamard and the control set, and you can assume that there is a Hadamard again to end this quantum syndrome measurement, and you do another quantum syndrome measurement with the same stabilizer and another data qubit. So you're just stacking up your syndrome measurement 4 times with 2 different syndrome measurement qubit, and then the 2 Hadamard gates in between these syndrome measurements are canceled out, so there's none here. So only the Hadamard at the beginning and the end is survived. So every time you do the syndrome measurement and take a measurement, you get the eigenstate, right? Based on the measurement outcome, you get the eigenstate. So, but we took the measurement at the end. So what we're going to get is, based on our measurement, this data qubit will become an eigenstate of these syndrome measurements. So if you take one syndrome measurement here and you got 0, that means your data qubit A is now collapsed into +1 eigenstate of Z, right? If you got 1 after taking a syndrome measurement of Z stabilizer, you got -1 eigenstate of Z, right? So I think we talked about this last time. So this stabilizer have 2 control Z here. So now if you have a data qubit AB as a 2 qubit state, and let's say you took a measurement here and got 0, then your data qubit AB contains 2 qubit state which has +1 eigenstate in ZA and ZB, according to ZA and ZB. So you cannot, in this case, you cannot separate your syndrome measurement each other. It has to be in a one single gate, ZA and ZB. So let's try to compute and see what really means. Or if you understood what I said, then you can check whether what I said was correct. So we have 4. This long expression. We're gonna collect 0, 0 from each part. So everything has zeros. Every part has 0, 0. Because see, it's a plus, minus, or minus, plus. So in the first summand, we have 0, 0 with the plus sign. So we're gonna take all of these. A0. Let's see. Okay, right. Let's write it out. Okay. 1 times B0, 0, B1, 1. And then in the second case, you can collect 0, 0 with the plus sign also. So everything is actually plus sign. So you just collect everything here without changing any sign. B0, 1, B1, 0, and then the third one, A0, 0 minus A1, 1, B0, 0 minus B1, 1, and plus A0, 1 minus A1, 0, B0, 1 minus B1, 0. So this kind of confusing notation. So I'm going to use the matrix representation of qubits. So let's say, look at this one first. This is tensor product of 2 qubit state. So we have A0, A1, tensor product, B0, B1. That's the first two qubit state. And the first one now, A1, A0. So be careful about the order here because it's now 1, 0, not 0, 1. And B1, B0 plus A0, A1 tensor, and B0, B minus B1 plus A minus A1, A0 and minus B1. B0, right? So let's make it into 4x1 matrix and combine all. We have A, so remember how we represent our quantum state into matrix? By tensor product, you do the dumb, I call it dumb multiplication, so not the usual matrix multiplication. So assume that this 2, 1 matrix is inserted in the first entry here with the multiple of A0. So we have A0, B0, A0, B1, A1. Now the second entry here goes here. A1, B0, A1, B1, and then A1, B1, A1, B0, A0, B1, A0, B0, and then A0, B0 minus A0, B1 minus A1, B0. And now it's plus A1, B1. And we have A1, B1 minus A1, B0 minus A0, B1, A0, B0. So what is it? So let's look at the first entry. You have A0, B0, A1, B1 twice. 2, A0, B0, A1, B1. And in the second entry, you have these two canceled out, and these two also canceled out. So we have 0 for the second entry. And the third one, we also have canceling. So it's 0. And the fourth one, we have twice of A0, B0, A1, B1. So it's 2, A0, B0, A1, B1. So what does that mean? So the phi 0, 0 is 2 times A0, B0 plus A1, B1 times. So if you take out this scalar here, it's 1, 0, 0, 1. So 1, 0, 0, 0 means that it's 0, 0, right? And 0, 0, 0, 1 is 1, 1. Okay. So these coefficients are set to be somewhat accordingly. So that so if you look at this state, maybe I should say so when I write this out, and I should have put 1/2 every other place here, and 2 here. So that whenever I take this quantum state for the data qubit, it's going to be normalized. But let's not forget, and let's not be too tedious about this coefficient. What's important is the quantum state, and the quantum state and what kind of base state it consists about. So I don't care about the size here. So it's just size. This number is about a probability, how much probability you have to observe 0, 0 when you have this. Well, I don't care if I have got this, then the probability don't matter. So I'm going to just say psi 0, 0 is whatever I get after the quantum measurement. It's plus 1, 0, 0 plus 1, 1. Okay, so that's what I get after I get the measurement outcome 0, 0. So what is it so special about this? As I said, let's look at this ZA and ZB. If I apply this to phi 0, 0, then so applying ZA and ZB separately, right? So it doesn't do anything on 0, 0. It does change the sign after each time it applies to here, because everything is 1, 1. There is minus 2 minus 1, so it's still plus. So it's going to be same 1/2, 0, 0. So it's minus 1, right? So it's 1, 1 here. And it's the same phi 0, 0. So you can see that phi 0, 0 is plus 1 eigenstate of ZA, ZB. And let's look at XA and XB. So now you change X and 0, and 0 and 1 here. So for the data qubit A, you change 1 and 0 here, so 1, 0, 0, 1. And then you change the data qubit for B, and 1, 0 becomes 0, 1 becomes 1, 0. So it's again it's 1, 1 plus 0, 0, which is same as psi 0, 0, right? So we can conclude that psi 0, 0 is plus 1 eigenstate of XA, XB, and ZA, ZB for both of these gates. How about phi 0, 1? What do you think? Oh. How about phi 0, 1? So it means that your measurement outcome is 0, 1. So it's 0 for X measurement, 1 for Z measurement. So it means that it should mean that the quantum state stored in the data qubit A and B has to be plus 1 eigenstate for XA, XB, and minus 1 eigenstate for ZA, ZB. That should be the case. So let's check. So psi 0, 1. Now again, let's collect all the 0, 1s, possible 0, 1s here. So in here, 0, 1 has plus sign. So I'm gonna just have the same thing here. So I'm gonna write it out as a 4x1 matrix right away. So it's A0, B0, A0, B1, A1, B0, A1, B1. And then the second one, if I collect 0, 1 here, 0 is plus sign, 1 has also plus sign, so it's also plus. So just take this coefficient here, or data qubit here. So what is it? A0, B1, and A0, B0, A1, B1, A1, B0, right? Yes. And then let's look at the third one. We need 0, 1. So I can take 0 with a plus sign, and now 1 has a negative sign. So I need to put the negative here, negative, and put everything here. A0, B0, A0, minus B1, and minus A1, B0, A1, B1. And the last one now, 0, 1, also has negative sign. So I get minus of minus A1 minus B1, so it's plus B1, and then minus A1 B0 and A0 minus B1 and A0 B0. Okay, times. Okay, so this is matrix multiplication, so we don't need time, sorry. So let's think about cancellation. So in the first row, we don't, let me check if the computation is right here and here. Let's see. Good, right? Yeah, let's see. Okay, so this one comes from the second one. Sorry, so I made mistake here. So we have A1 as a coefficient of cat 0. So it has to be A1 here, and A1 B0, and then now A0, right? A0. Okay, so the first one we have canceling out, this one and this one. Okay. And the second one, A0 B1, A1 B0. Now in the plus A0 B1, so again the same thing. And then plus A1 B0, so we get the twice of the same thing. So on the third one, we have A1 B0 plus A1 B0, the same thing again, and A0 B1 and plus A0 B1, same thing again, so that also survives. And A1 B1, A0 B0, so the minus A1 B1 canceled out, and A0 B0 canceled out. So in the second and third, we have the same coefficient. So let's put it together. So we have 2 A0 B1 plus A1 B0 times 0, 1, 1, 0, right? 0, 1, 1, 0. So two base state for 0, 1, 0, 0 and 0, 0, 1, 0. So that means we have 0, 1 and 1, 0 survive. Okay. So again, this coefficient only means for the probability. Once we take the measurement, it will collapse into the quantum state of strength 1. So I don't care about the coefficient here. So just take these two quantum states. The only important thing is they have the same coefficient. There are equal chances. The only way you can make it is 1 over square root of 2, 0, 1, 1, 0. Okay. And let's do the same thing as we done for the psi 0, 0 there. So we have ZA, ZB, psi 0, 1. What is it? So we're applying Z to A data qubit and B data qubit, the first one and second one. So we have nothing going here, nothing happens here because it's 0 for data A. But here, data A is cat 1, so it changes the sign. So it's going to be plus minus when I apply ZA. And when I apply ZB, now the first one changes the sign because it's cat 1. But no change of sign for the second one, but it's already minus. So it's 1 over square root of 2 minus 0, 1 minus 1, 0. So it's minus of the original quantum state. Minus of, sorry, can't read it, right? Can you read it if it's too far here? So it's minus psi 0, 1, okay? So how about XA, XB? So it only changes 0 and 1. So it changes 0, 1 here, so it's 1, 1, 0, 0, and then you change the 0, 1 for the data B, so it's 0, 1. So it becomes 1 over square root 2, 1, 0, plus 0, 1, right? So same thing. So you can see that this phi 0, 1 is plus 1 eigenstate for XA, XB, and minus 1 eigenstate for ZA, ZB. Okay? So you can do the same thing for other state, phi 1, 0, phi 1, 1. So let me summarize this. So phi 0, 0 was square root of 2, 0, 0, 1, 1. And phi 0, 1 was square root of 2, 0, 1, 1, 0. And phi 1, 0 and phi 1, 1. So what do you think the phi 1, 0 should be? So you want minus 1 eigenstate for XA and XB, plus 1 eigenstate for ZA, ZB. So try this out. We have 0, 1 minus 1, 0. Is it right? So if you look at the XA, XB, it's going to change the 0, 1 here and 0, 1 here. So it's going to be 1, 0 minus 0, 1, which is minus of original. So, and ZA, ZB, it's going to change sign for here. It only changes the sign for here and here, right? Let's see, it's confusing. It's a bit, so when I apply ZA, ZB, ZA, ZB, so when I apply ZA, it's plus here, and when I apply ZB, it's minus here. Oh, it looks like it's 1, 1, right? So it looks like it's 1, 1, right? It changes the sign in both cases. So XA, XB changes the sign. ZA, ZB also changes the sign. How about the last one? So the last one is, it should be phi 1, 0. It should be 0, 0 minus 1, 1. So let's see. If I apply XA, XB, then it becomes 1, 1 minus 0, 0. So it changes the sign. So now it's 1. And if I apply ZA, ZB, then it's still same thing because we have 2 minuses on the second, right? So it's 1, 0. So these are 4 states after you measuring the measurement qubits into 4 possible outcomes. And you can see that these 4 states are actually orthogonal to each other. None of these quantum states are overlapping in some ways. So these becomes basis of the Hilbert space of 2-qubit state. So originally we take a basis of 0, 0, 0, 1, 1, 0, and 1, 1, but this is another base state, which are all entangled. And so how do we use this to detect an error? So here's how it works. So the third step now, remember I listed 1, 2, 3 here. We finished up to 3, so we run the circuit and we take the measurement, and we will get one of these 4 quantum states stored in the data qubit. So measurement qubit is already used. It's already measured. So whenever you measure it, it's collapsed into the measurement outcome, right? So it's really it's not going to be used as something that stores the quantum information. You can you already know that what is the measurement outcome, so you can just assume that the measurement qubit is of that state from now on. So you want to run the circuit again. You want to run this circuit again with the given measurement outcome, assuming that that outcome is the initialized state of X measurement gate and Z X measurement qubit and Z measurement qubit. So now AB is one of these states, right? But we didn't measure it. That's the catch. We didn't measure it, but we know what that is. And now let's run the circuit again. If there's no error, any error on data qubit A or B, what will happen? Suppose that we have 0, 0 as a measurement outcome, which means that the X stabilizer qubit and Z stabilizer qubit is initialized as cat 0. Okay? So that means AB data qubit is entangled like this. Okay? So you run the circuit again. What will be, if there's no error whatsoever, and there's no error, perfect quantum circuit, what will be the measurement outcome? 동현? If you read 1, 0, 0 and you stabilized your data qubit, you run the circuit, and we assume there's no error, what will be the measurement outcome? Anyone? So we talked about this in the past 2 classes. Same as original, right? 0, 0. Okay. Why? Because the data qubit is already plus 1 eigenstate of ZA and ZB, and plus 1 eigenstate of XA and XB, right? So we're looking at this all possible state when we do this, which is plus or minus eigenstate of ZA, ZB, and XA, XB. But this data qubit is already stabilized as plus 1 eigenstate and plus 1 eigenstate for these 2 gates. There's no other outcome. There's no other possibility of getting minus 1 eigenstate or of ZA, ZB, or XA, XB, right? So if there's no error, whenever you apply this circuit, it's gonna be always the same result, 0, 0. But now let's assume that there is an error. Let's say error occurred here, Okay, it could occur somewhere else. I mean, it could occur here or there or whatever. So let's assume they occurred here. What will be the measurement outcome of X stabilizer and Z stabilizer? Just a short quiz. It was 0, 0, and this is after we ran the circuit once in the beginning to initialize our data qubit, and it is initialized as +1 eigenstate of XAXB and ZZB. Now we ran the circuit second time, and we kind of know that the X error has occurred in the data qubit A before we take a circuit. Okay, so it's right here. What will be the measurement outcome? 1, 0, 1, 0, 1, 0. Ah, okay, so the reading from X to Z, so it's going to be 0, 1. Why? Yes. X error. Yes. Right. So now data qubit, it's not applied on B. The X error is not applied on B. It only applied on A. But A is now changed to something that is opposite eigenstate of original, because it was originally the eigenstate of Z, but whenever you apply X to the eigenstate of Z, then it changes the eigenvalue to the opposite value. So let's look at this with the example here. So if you have kind of XA, the error occurred on your phi 0, 0, then you're changing these two, right? So we have 1 over square root of 2, 1, 0, plus 0, 1. What is it? Where is this? Here, phi 1, 0, 0, 1. Right? So when you have this error, your quantum state on data qubit AB changes to quantum state whose eigenvalue is +1 eigenstate of XAXB and -1 eigenstate of ZAXB, right? So therefore, the readoff must be 0, 1, right? That's how we detect an error. We don't know, we don't actually know exactly when this X appeared. So if it was appeared on here, then we will detect it at the third step. But maybe the X was appeared in between the first cycle, the first applying of this circuit, and the second applying of this circuit. And then it changes the data qubits, so to this quantum eigenstate. So therefore, it has to be detected on the measurement qubits. So when we detect the change of a measurement outcome, we know there must be an error. We know that there should be an error. But now, the question is, what happens when we have two errors here? So it was originally 0, 0, initialized as +1 eigenstate. And let's assume that there was two errors. What will be the measurement outcome? What's the eigenvalue of the original state, phi 0, 0, with XAXB? It's +1, which means it doesn't change the state, right? So when you have two measurement outcome, two these errors, then it's the same thing. When you just look at this, what happens to this quantum state? It becomes just as applying XAXB on your original state. It's the same thing. So in that case, you cannot detect an error. So we're kind of assuming there is an error, arbitrary, artificial error, but we don't know that error exists or not. So we only can detect the existence of error. So in this case, we don't know, we cannot detect an error. So it's the same outcome as if there's no error at all. So it's kind of a failure of detecting an error, right? So So the quantum error correction is not 100% correct, and every error correction is not 100% correct. There's no 100%, but you want to increase the percent chances of getting success of error detecting or error correcting. But in this case, it's an error. It's a failure of the error detection. And you can do the same thing with the Z error when you have a Z error. So how about this? Suppose that you have Z error instead of X error on here. What will be the measurement outcome? So X error changes the measurement outcome to 0, 1, because X error is detected with the Z measurement gate, and Z error is detected with X measurement, syndrome measurement, right? So it will detect it on the X stabilizer. So, well, you can check again. So it's, if you want to, so XA, ZB, let's see what happens here. V0, 0. So first of all, it changes X. So it's 1, 0, and 0, 1. And ZB, it only it changes the sign for B, right? So we have plus originally, but it becomes minus. And what is this? 1, 0, minus 0, 1. So it only differed by minus 1 sign with the phi 1, 1, right? So that's it. So minus 1 change only differ by the phase, the entire quantum state, the base state. So it's going to be just the same. So it's phi 1, 1, phi 1, 1. So you can see that the measurement outcome will change it to 1, 1. So if you get, now you can see that the pattern here, you're going to detect, you're going to measure your stabilizer qubit X and Z separately. And whenever you get change of the value, change of the bit that you read from X stabilizer, you can see that you know that there's a Z error occurred in the A and B data qubit. If you detect a change of your measurement outcome on Z stabilizer, you know that there is a X error, one of X error occurred on A or B. So it does not mean that if you read no change on X stabilizer and Z stabilizer, there's no error whatsoever on the data qubit A and B, because it could be both data qubit had the same error, so that each error affected the change once, so the change twice, so that 0 becomes 1 and 1 becomes 0, so get to original. So it's not detected in that case. So this is kind of, as I said, the simplest surface code. So it can detect one X or Z error on A and B by detecting change of measurement outcome of X and Z stabilizer. So we can say that there are two functionality of X stabilizer and Z stabilizer. One is to initialize the quantum state before you begin the error correcting process. So I'll give you, which means that so when you first run the circuit with the random quantum state here, then after you run the circuit and take a measurement, you have no control of what is going to be the outcome, what is going to be the final data qubit stored in A and B. So it's going to be just set as a default, whatever it comes. So if it's 0, 0, then that's the default state. If it's 0, 1, then this is the default state. The default state is the original state that you consider as the initialized quantum state. And the second functionality of the stabilizer qubit is detection, of course. So, so this is the simplest one. I'll give you a little bit more complicated one. So you're gonna, the good thing about this surface code is that it can scale. You can make it bigger. So how do you make it bigger? You just attach more stabilizer and data qubit in this pattern. So we have X, data qubit, X, data qubit, X, data qubit. So actually, it has to be the opposite direction. So we have here A. So in order to make it similar to what this is, so this part, this small piece, I assume that this is on the right top corner here. So A, Z, B here. So AB is just to indicate that this small piece is right at the top right corner of the bigger one. So I'm not going to label the other data qubits here. So it's going to be, let's see, another data qubit, that data qubit. I think that's it, enough. So X data qubit, X data qubit. Yeah, well, that's bigger. Let's make it bigger. X data qubit, and Z here, and Z here, and here we have data Z, data Z. And again, we have data Z, data Z, data, and X, data X, data X. And connect everything here. So it's not even so this is slightly bigger than the one next to the simplest one here, but this is still not big enough, but this is what I can draw in the blackboard. And you can see the pattern here. So there are, so in that case, so for each stabilizer qubit and data qubit, there are two types. One is the one that is inside. One that is inside, it is connected to every other 4 type of qubits. So stabilizer is connected to 4 data qubit. Data qubit is attached to 4 stabilizer qubit of different kind in pairs. And there are other qubits on the boundary here. On the boundary, this data qubit is only connected to 2 stabilizer, and this stabilizer is only connected to 3 data qubits, and so on, right? So what happens here? We do the same thing here with the same, more complicated circuit. We cannot draw the circuit for entire thing. So what happens individually is the following circuit. If you're looking at one particular stabilizer, let's look at this one, in the middle one. Let's say A, B, C, D. Just to label the data qubit next to X. You run the circuit X, A, B, C, D, H, X, B, C, D, and measurement at the end. So if you just take the quantum circuit for these 5 qubits, that's how it looked like. So there are going to be lots of more, but just these 5 qubits looks like this. So you can see that each of the state is the syndrome measurement circuit. So you take a syndrome measurement with X and A, X and B, X and Z, but you take a measurement at the end. So when you do this and take a measurement, you can assume that this data qubit ABCD right next to X stabilizer is collapsed into the +1 or -1 eigenstate of X stabilizer right here. So this X stabilizer has, let's say, measurement outcome C, then this psi A, B, C, D at the end. Okay, so let me write it here. If you take a measurement, so suppose that you pass this measurement stage, then whatever that is in this 4 data qubit is C eigenstate of XA, XB, XC, XD. Okay? So we are not saying that data qubit A is somehow eigenstate of XA. We have to look at it as a whole thing. This XA, B, C, D is of eigenstate of this XA, XB, XD. And since this is not the entire quantum circuit, we have to look at it as a whole. So how many data qubits? There are so many, so I can't count. But this whole data qubit is stabilized or collapsed into eigenstate of these big gates. So how many X gates we have? So every time you have a stabilizer and a pairing with other data qubit, you have X gate here. So for each X gate and for each B gate, you collapse into one big gate, and then you run the circuit. You run the circuit, this kind of circuit, for every single stabilizer, and then take a measurement outcome. You're gonna have a list of +1 and -1 or 0 and 1 for each stabilizer, and that's gonna be your signature of the eigenstate that is collapsed into the final data qubits here. So there's a reason why we put the order ABCD that way. So here, look at this. A, this is first, and this is second, and this is third, and this is fourth. So when you run this circuit, we do all synchronized way. So when I look at this the data qubit on the west of the stabilizer, I do this for every stabilizer. So this one is west to X, and this data qubit is west to X, this X stabilizer. And also this one is west to this Z stabilizer and here. So when the first part is running in your circuit, like this one right here, then you want to synchronize all the control C0 gate to every other here, every other C0 gates attached to the measurement qubit. So here and here, here. So this is all one. So when you design the surface code, you have to be careful if the stabilizer have 4 full data qubits attached or some data qubits are missing. But in this case, here, this stabilizer is missing the west data qubit. There's no the data qubit on the left. So in the first stage, this stabilizer do nothing. So you have to align your C0 gate for this stabilizer so that it's not doing anything when the other stabilizer is doing C0 gate to the left. Okay? And do the same thing for here, so in the second and third and fourth. So if you get this 2 second data qubit measurement, so this one, so on the north data qubit, you do the same thing here. So you get the north here, everything north applies here and here, right? And the same thing applies. So here, this one has no north data qubit, so it's gonna skip that step. So once you run this for west, north, south, east, then you use all the link between the data qubit and the stabilizer, and the circuit is complete. And you take the measurement, and you're not missing any of errors occurred in the data qubit to detect it on the stabilizer. So that's the basic step. We still need to talk about more because how do we detect an error? Well, the same way. So what happens when I have an error in here? Data qubit. So let's say if I have an error, let's say I have an error on here. Let's say X error. I have X error here in this data qubit. So we can only detect the error on the data qubit. We're not talking about the error on the stabilizer. So error on the stabilizer is considered as a measurement error. So it's not proper error. So people do count the measurement error as in the simulation, but we don't consider that right now because it gets it's just about simulating the settings in your simulation. So in the detection case, we only talk about the error on the data qubit. And suppose we have an X error, it's not detected on the X stabilizer. It's not detected on the X stabilizer. It's detected on the Z stabilizer here. Okay? So again, we don't know where the error occurred. Okay? So if this error occurred, then Z stabilizer will read off the measurement outcome of Z stabilizer here and here will change from the previous readout. So therefore, we know that, okay, this might be the data qubit that has X error by looking at the changes of the stabilizer readout. So now the question is, as I said, we don't know where exactly the error occurred. So suppose that so I'm gonna put the red mark here where the value is changed here. So if these two stabilizers changed its readout, then there are two possible ways of having these readouts changed. One is having X error in here so that it changes these two stabilizers. And also there could be these two data qubit has both X error. So this X error changes the readout of this, and this X error changes the readout of this, right? So we don't really know what is the case. But let's see, we can count the chances. So if you have one X error in here, that's one possible error on one data qubit. If you have two errors on these two qubits, that's the square of the possibility of having error on each data qubit. So if the data qubit has an error rate of p, then having error on here is p, but having two error on these two qubits is p squared. So we assume that p is always less than 1, right? I mean, quite less than 1, let's say 0.2 or something, like 20%, let's say. Then, well, it's logical to conclude that to go for the higher chances, right? We have to assume that it's more probable. It's more probable to have one data qubit error than two data qubit error at the same time. However, well, that may not be the case. But like a very low chance, it could be really the two data qubit error. So then, let's see. It gets interesting. I'm gonna talk about this more next time. This was actual error occurred. This is the data qubit that actually error occurred. But we kind of misjudged that these two data qubit has been corrupted with the X error. So let's say we corrected our error on these two data qubit, which has no error at all. So then what happens is we have X error, original X error, and our artificial X correction has applied on these two data qubits. So therefore, we have X, X, X on these chains. We have X, X, X here. So we kind of made our chain of X errors. So these two X's are error made by us, and this is the error actually occurred. So whatever that is, we have X chain of X occurred in here. So then it's kind of failure, right? We have an unwanted X chain of errors occurred in our data qubit. So instead of correcting it, we changed our data qubit into some different state that is not supposed to be. So that's a failure of our X error detection. We're gonna talk about this more because there is something that I missed in this lecture, which is important about the loop and the chains here. So next time I'm gonna show you my simulation code, and then I'm gonna visualize the surface code more.